Green's function. British mathematician George Green developed the concept of Green's function, and this method is used to find the solution of a non-homogeneous or inhomogeneous differential equation like del square psi is equal to rho by epsilon 0, where rho by epsilon 0 is the source function. The previous classes we discussed about how to solve the homogeneous differential equation by using the variable separable method. Okay, now it is this Green's function is used for solving the inhomogeneous differential equation. And first we can discuss the properties of Dirac delta function. We already know the properties, that is integral all space delta x minus t into dx equal to 1. This integral is equal to 0 except at x equal t. So at x equal t it has some value, otherwise this integral is 0. The next is integral delta x minus t ft dt is equal to fx. Now suppose Green's function can be, we can represent it as g of xt. Suppose g of xt is the Green's function, then when differential operator L is the differential operator and this operator is operating on this function, then we get the value, that is L gxt is equal to delta t minus x, or L gxt is equal to minus delta of x minus t. This property of a Green's function can be exploited to solve differential equation of the form L of ux equal to fx, where fx is the, I already told you that it's a source term. Okay, it's not a it's not a homogeneous differential equation. Now, one-dimensional Green's function and its properties. Green's function is an integral kernel that can be used to solve differential equations from a large number of families, including simpler examples such as ordinary differential equation with the initial or boundary value condition, as well as more difficult example such as inhomogeneous partial differential equation with the boundary condition. So Green's function can be used to solve the ordinary differential equation, okay, or inhomogeneous partial differential equation with a boundary condition. In case of both the differential equation, we can use this function. Now L gxt is equal to minus delta x minus t. Taking L is the L is a self-adjoint operator. Suppose this operator is acting on this function. Now this operator is d by dx of px of d by dx plus qx, and this operator is acting on this g of xt. Okay, that is d by dx px d by dx of g of xt plus q of x g of xt is equal to minus delta x minus t. Okay, now integrating this equation over x for small interval, that is t minus epsilon to t plus epsilon. It's a very small quantity. Epsilon is a very small quantity and you can integrate this. So I just integrated this one. Okay, this equation. I integrate this equation. Epsilon is a small quantity and the second part is a 0, and then this part is equal to 1. Okay, RHS is 1. We use the property of Dirac delta, and epsilon is small quantity, then this RHS is 1 and this part is taken as 0. Then this will become integral of a derivative of a function means this derivative itself. So p of, and applying the limit. Okay, and applying the limit, upper limit and lower. Upper limit is t plus epsilon, lower limit is t minus epsilon. Okay, and I applied this limit, and in the limit epsilon tends to 0. If epsilon tends to 0, then this equation reduced to in this form. Okay, now dg by dx dg by dx at t plus epsilon, that is upper limit, minus dg by dx at t minus epsilon is equal to minus 1 by p of t, that is dg2 minus dg2 by dx minus dg1 by dx equal to minus 1 by p of t. So this property shows that the values of Green's function must be different for x less than t and x greater than t. So Green's function is, the value of Green's function is different for if the value, if x is less than t, it has some value, and if x is greater than t, and it has some value. So we have to label the Green's function before t as g1 xt and the Green's function after as g2 xt. So this equation can be written in this form, that is g2 x comma t plus epsilon minus g1 x comma t minus epsilon is equal to 0. And at x equal to t, g1 is equal to g2. And in case of one-dimensional Green's function, these are the important property. The first one is the Green function is continuous at, if at x equal to t, g1 is equal to g2, that is Green's function is continuous at a boundary, and the derivative of Green's function is discontinuous. These are the two properties of one-dimensional Green's function. Now symmetric property of Green's function. If there are two variables that are r1 and r2, then the symmetric properties of Green's function states that g of r1 r2 is equal to g of r2 r1. Okay, so we have to prove this. For that, let's Green's function g of r comma r1. Okay, not r1 comma r2 or r2 comma r1. It is g of r comma r1 satisfy the equation with a point source at r1. That is, suppose here is a point source q and this distance is r1. Okay, then it satisfy the, okay, here use the one-dimensional operator. Okay, d by dx and all. Here we are using the three-dimensional, okay, three-dimensional form. That's why I used delt. So del dot p of r del g r comma r1 plus lambda q of r g r r1 is equal to minus delta r minus r1. That is equation number 2. Now if the point source is at r2, if the point source is at a distance r2, then the corresponding Green's function. So instead of r comma r1, I used r comma r2 here. Okay, so that is equation number 3. Now multiply 2 by g of r comma r2 and equation 3 by r comma r1, then we can subtract. So I just multiplied this r comma r2 with the equation number 2. Okay, so that is equation number 4. Then we can multiply equation number 3 by g r r1. So I multiplied here, I multiplied. Okay, never written. That is equation number 5. Now 4 minus 5. We are subtracting 4 minus 5 here. This term and this term. It is 0. Then the other terms, I wrote the other terms here. Then we can integrate the equation of the volume V. I integrate this equation. I put the symbol, and d2 is the small volume element. Okay. Now we can change the, we have to convert the volume integral into surface integral. So we can use the Stokes theorem or Green's theorem. So this is the form of Green's theorem. Then equation number 6 becomes, 6 is this one. This is the equation number 6. But according to the boundary condition, g of r comma r2 and g of r comma r1 have the same values on the surface. It has the same values on the surface. So normally this term will be 0. LHS part will be 0 because g of r1 r2 and g of r comma r2 and g of r comma r1 have same values. So this part will become 0. Therefore this is equal to, RHS equal to 0. Therefore g of r comma r2, r1 comma r2 is equal to g of r2 comma r1. So this is the Green's function. So we can prove that the Green function is symmetric.